Good morning, everyone. So welcome back to QX01, Introduction to Quantum Information and Associated Technologies. So let's have a look at the planning for the next few weeks, especially that there is a change compared to what I showed you last week. So far we've done 4 lectures. So first one, an introduction to quantum information and technologies. Second one on classical information and computation. Then the third one where we introduced the qubits. Then last week we looked into multiple qubits and the notion of entanglement. And today we will look into what we call operators and the measurements associated to them. So I actually already swapped that. Before it was written measurements and operators, but actually, as we will see, I should really say operators and measurements. So the change is that next week, there is no lecture, as opposed to in 2 weeks' time. So next week, no lecture. The week after, it will be on quantum gates. And the week after that, it will be given by people from the company QX01, which is a British company, on quantum cryptography, although it's not going to be live, but it will be available on YouTube afterwards. It's going to be live for our students, but not live for the rest of the world. But it will be available on YouTube afterwards. And then we will start on quantum algorithms and so on and so forth. Right. So before we go on to operators and measurements, we are not quite done with what we talked about last week on multiple qubits and entanglement, because there was something I said I would talk about, which I started but didn't finish, which is the actual physical meaning of psi. So this wave function actually has a physical meaning. So the physical meaning, so what I introduced is actually one of the postulates of quantum mechanics, quantum physics. The first postulate in quantum mechanics tells you that whatever quantum system, whatever particle, whatever anything, again, you, me, a table, an electron, an atom, we can associate, or it is defined rather, by a function of space and time, which we call psi, which we call the wave function. So everything is defined by a wave function. And this wave function can be represented by one of those quantum state vector, these QX. Therefore, we know now how to write it. This wave function is therefore a complex function, as we saw, that we work in complex space. But like I said, so this has an actual physical meaning as opposed to a ket, which could be just a mathematical tool. And the physical meaning is that you can define the probability of finding your system at the position r and time t in a volume dv, and that probability is given by psi star times psi dv. That's the probability. So we will come back to the notion of probability today, but this is a probability in quantum mechanics to find your system at the time t at the position r in a certain volume. And of course, if we integrate over the entire universe, this quantity here, then this is our normalization factor, which states that the integral of this quantity here over the entire universe will give us 1. So in other words, if I look into where that system is and when an entire universe, then I will find it. Okay, that's the postulate that sounds like a fair one. But the point is that, so there is a physical meaning to this wave function. It's what defines everything, so it's rather a strong physical meaning. And therefore, as I said before, the fact that we use bra and kets and etc. Is not just a mathematical tool. It is a very convenient one, but it's also because behind there is an actual physical meaning to our system. So the bracket notation has a physical meaning, but therefore we can say that this wave function lives in a Hilbert space. We talked about Hilbert spaces, what how they are, what they are, this particular geometry. They are, so it's a complex function in general. We can define, like we did for bra and kets, we can define an inner product, or a scalar product, which is a bit different than the standard one, as we said, which would be psi star psi, if it's the same wave function, but we can also multiply two quantities with two different wave functions, so phi and psi. On the left-hand side, we don't forget to put the star. And we have a correspondence, as I said, so psi on the right-hand side is a ket, and phi star on the left-hand side is the bra associated to it. We can normalize, as we said, so we have the normalization function, so which is this notation in integral notation, as we just saw. And this is what? Well, this is the bra times the ket associated to it, and that gives us the normalization factor. And we can generalize by saying that this structure here, phi star times, phi star times psi, is the bracket phi psi. Okay. So we have, as I said before, so we have sort of a mathematical representation equals to, so over the entire volume equals to phi star times psi of an entire volume, and this is a physical representation. So in other words, the qubit, the bracket notation and the qubit formalism, is used for quantum physics, for getting quantum technologies. So this very representation has been developed in the 1920s and 1930s in order to be useful, to form useful tools to deal with quantum physics. But it turns out to be very convenient for quantum technologies, as we saw a little bit, and we'll see more and more, to treat qubits and so on. And then afterwards, once you have this, once you have this structure where you have the left-hand side and the right-hand side that are not symmetrical, then you find that again where you have the left-hand side, the left-hand side and the right-hand side that are not symmetrical. Then all the rules that we saw previously applying to brackets with the notion of dual space, then you can use them the same way for the integral notation if you look at the physical meaning to it. So you can use, again, the same manual as we saw before, and use all these different rules and conditions and so on for our physical representation in our physical system. And of course, if we have a physical system, so I have to give you a bit more on the physical system, is that this wave function psi, it's given for a given system, but like we have in classical physics, so in classical mechanics, we have Newton's law. So if I consider something, a system with a mass m, then Newton's law tells you that m times the acceleration of the system is given by the sum of the external forces that apply to this system. And Newton's mechanics tells you that if you know that, then you basically know your system. You know how it will behave, you know how you can predict how it will behave, and you can tell what happened to it. Well, we have an equivalent in quantum mechanics, which is the Schrödinger equation. And the Schrödinger equation is this time an equation that drives the behavior or what happens to the wave function psi as a function of time and space. So Schrödinger equation is this equation. So we'll come back to it, although not too much, because this is, well, you need that if you really do quantum physics, but in quantum technologies, you don't need that formalism that much. But just to give you an idea, so what we have here is we have h, a function h, times the wave function is equal to I h bar, which is the reduced Planck constant, and we already talked about, times the derivative in time of the wave function. Okay, so this Veillot equation here is the exact equivalent to this one, but for a quantum system. Okay, it's equivalent, so Newton's law tells you have a classical system. I apply Newton's law, and I can end up with the physical property of my system. Well, quantum mechanics is I have the wave function of my system that describes the system, and the Schrödinger equation, this equation, will tell me how the quantum system will evolve in time and space. And just a quick word on this function h. This function h is what we call the Hamiltonian, and with the notation of a little hat on top, and that's what we're going to talk about today. And h is an operator, and what is h is the total mechanical energy of the system. So the equivalent, again, to classical physics. In classical physics, you can define the energy of the system, which is made of two terms, the kinetic energy term and the potential energy term. This forms the total mechanical energy, which we usually call the Hamiltonian, as a rather more general how should I say, convention and system and mass behind the simple Newton's law. Okay, so it's the Hamiltonian formalism in classical physics is a more generalized way of treating classical physics. But now, in quantum mechanics, this Hamiltonian function, this h function, this operator, which we will see what that means, will define how this quantum system behaves in space and time. Just a quick word, a cultural reference. So in France, the kinetic energy is usually written like this, because it's energy cinétique with a C. So that's the French version. You can see that there's a C, as opposed to the English version, which is the kinetic energy with a K. So the compromise I found is to call it the kinetic energy, of course, but to write it EK rather than K or EC. Potential energy, that doesn't change. It's a P in French and it's a P in English, so that's fine. Right. So we'll come back to what actually is, what does it mean, this Hamiltonian function in more physical systems later on. But for now, that's all we need to know. And so what we just saw is that this observable, Hamiltonian, I can actually define other observables. I can make measurements which are Hermitian metrics. So I put here an example that we already saw, where we start from a qubit, a wave function in Ket notation. We apply, in this case, a Pauli matrix, so a gate, as we will see next time. We can apply 1, we can apply 2, and the system will evolve in time as we apply the different gates and as we, in terms of physical meaning, as we sort of change the Schrödinger equation in time. And at the end, so we'll come back to that very soon, next time, we can define the equivalent of Schrödinger equation in a way, but in a circuit notation where we have our psi function, we have some qubits, we will see this is an entangled gate between these two, or these two. Then we apply another gate. This one, H, is not Hamiltonian, is Hadamard gate. We'll come back to that later on. We'll make a measurement, so on and so forth, and we end up with an output here. And as yet again, a quick sneak peek, this quantum circuit that we will study is actually the circuit for quantum teleportation. Okay, so remember I told you at the first lecture that quantum physics actually tells you that quantum teleportation is possible. Whether this type of teleportation is possible, that's another story, but at least this one is possible, and in fact has been done and is done now pretty much on a regular basis in different labs. Right, so that's what I wanted to say on the physical meaning of psi and how it behaves, and we will come back to that and how there is a mathematical representation to something that is physical. Good. So now let's go back to what we want to address today. So today we want to address operators and measurements. So we already just had a quick view on what it is. And we will address 5 points. So the first one will be what are operators in quantum mechanics, first of all. The second one is, as I promised before, is I will introduce as a toy model or perfect model of all of what I'm going to talk about today, the spin state of an electron. So I will introduce what that is, and we will use that as an example for today. Remember, I told you before that I'm not going to talk about all the physical implementations that there is in quantum technologies. I will focus on 2, which is the photons, so photons as qubits, and spin state of electrons as qubits. So I introduced already the photons are as qubits, and today will be spin state of electrons. And then I will talk about the notion of measurements and what we call the collapse of the wave function. And this is a very sort of dramatic vocab that we use in quantum physics, but you will see that it has a really important meaning. And then we will talk about the mean value of an operator. So the mean value of an operator is actually what, if I make a measurement on something, what is going to be the outcome, the actual measurement. I come up with something that measures voltage or current or an electron, a spin state. And this is a measurement. What is going to be the expected outcome, the measurement I will find. We will see also the notion of commutation, and in particular that as opposed to classical physics, in quantum mechanics we will see that if you make measurements, so if you make a succession of two measurements, so A and B, say, then sometimes the order matters. So if you measure A and then B, you might not find the same result as if you measure B and then A. Okay, so that's a very important notion. And then finally, we will finish with the notion of outer product. And remember, we left that aside as a what is this new object, but we will define it today and use it today. Right. So operators in quantum mechanics. So this is actually the postulate 2 of number 2 of quantum physics, quantum mechanics, is that to every observable in classical mechanics, so observable in a sense that to everything that you can measure on your system, be it polarization state of a photon or the current or the spin state of an electron, so to every observable in classical mechanics, we can, so when you make a measurement, we can define an operator which is going to be a linear Hermitian operator in quantum mechanics. Okay? So basically, an observable in the real world has, which we could expect, a representation in quantum mechanics, which we call an operator, and this is given by, as we will see, matrices. So here I put examples of such operators. So here's a classical observable. So if I give you a particle, you could measure its position x, along x. You could measure its momentum, px. A quick word on momentum. As opposed to the speed. So in classical mechanics, we like usually the position x and the speed, say Vx along x. But we also define in classical mechanics the momentum, which in classical mechanics is equivalent. So momentum, which is P of x, which is m, the mass of the system, times Vx. That's in classical physics. And so for the position, we have the operator x associated to the position. And remember, we said when we start to introduce operators in quantum mechanics, we don't have to, but most of the time we like to put a little hat on top to show that this is an operator as opposed to a simple number. It could be x as x equals 3. No, here it actually has a physical meaning, which is an observable of the position x. So this operator has to be specified by the little hat on top. So that's for position. But for speed, so we can define the momentum, which is the equivalent in classical physics. But in quantum mechanics, we have x hat, but we work on px hat rather than the speed. And this operator now is actually a constant, so minus I h bar, which is a constant that we find regularly in quantum physics. You already saw it appearing in Schrödinger's equation. And then we define it by a derivative, a partial derivative to x. Okay. So we already see here that this entity, quantity, this operator, has no meaning, in a way, on its own. Okay? It has to be associated to something. So to the wave function, for instance, which we said can be a function of position. So if it's in 1D, it's a function of x and t. And that makes sense now, because that is what is minus I h bar, derivative of this function psi with x. Okay. It's not so. We will use these two operators later on for when we will talk about commutation, but turns out to be not used so much in quantum technologies. So we're going to talk about it today, but we're not going to talk about it too much afterwards because, well, we don't have to deal with these operators so much in quantum technologies. And the main reason for that is because these operators of position and momentum are continuous operators. So they have a continuously, so in terms of measurement, you can find an infinite number of results for the measurements. So the space, the Hilbert space associated to it, I remember I said that before, is of infinite size. And that for quantum technologies is not something we like because we want to handle qubits, well-defined qubits. We want to make operations on them. We want to make gates on them. So we have to have a more constrained Hilbert space to work on and a discrete one. So that's why those aren't. But it's interesting to introduce them, and especially when I will talk about later on about commutation and showing you how in quantum physics, two successive measurements, the order of two successive measurements is not always the same if you swap the measurements, the order of the measurements. So to carry on, so other examples, so we have the total energy of the system, the mechanical energy of the system. So we know now, we have these operators that we call the Hamiltonian H, and this is the sum of two terms, which is the kinetic energy plus potential energy being something that is applied to our system. We will see some examples of that later on in the semester. And here are some others, and especially one that we will look into quite extensively today, which are angular momentums. So I will talk about angular momentum in a minute. So we can associate an operator of an angular momentum L the same way in quantum mechanics. And in particular, if I define, which I'm going to do in a minute, the notion of spin of an electron, I'm not quite sure, S, the spin S of an electron, then I can associate an operator to it as well. In fact, the spin of an electron is also in a broad way an angular momentum. It's just a particular physical property of the electron, but it actually behaves the same way as any angular momentum, which are very important quantities in quantum physics and in quantum technologies in terms of transposing to gates. And operators are linear emission matrices, like the Pauli matrices. So therefore, all these operators should follow this rule of emission matrices. So if those operators are matrices, then mathematically we can find, this is linear algebra, we can find the, so if this is linear algebra, standard one, if I have a matrix A, I can try to find out the eigenvalues and the eigenvectors. So the eigenvalues would be lambda here, and the eigenvectors V associated to this matrix. Again, just a quick word. So eigenvalues in French are called valeurs propres, and so proper values as opposed to eigenvalues, and eigenvectors are called vecteurs propres, so proper vectors as opposed to eigenvectors, whatever. So that's what I would do. So the eigenvalues would be the lambdas, and the eigenvectors would be the V's. And if I transpose that in our Hermitian spaces, in our Hilbert space, sorry, with our operators A, so A is any of these operators here. It could be any of those plus others that I haven't listed here, but there are other physical observables that have operators associated to them. And I can find the eigenvectors. In this case, they are kets, and the eigenvalues, lambda, which are complex numbers, which are the eigenvalues of the system. And for finite dimensions, so eigenvalues, I will find as many as the dimension of the Hilbert space associated to the matrix. It could be eigenvalues that you find several times, but they are as many as the space of the matrix, which is the same in linear algebra. If you have a 2x2 matrix here, then you got 2 eigenvalues and 2 eigenvectors. And the eigenvectors, likewise, you have as many as the dimension of the matrix. In order to find these eigenvectors and eigenvalues for operators, then what you do is you would do the same. You would find the determinant of AV minus lambda V, and you look for, so that equals 0, and you look for which vectors in which values lambda this actually works. Okay. Except that now, as opposed to linear algebra, where those are just vectors and numbers, these eigenvalues for our operators here, and these eigenvectors for our operators here, so these V and lambda, have physical meaning, as we just said. What are the eigenvalues? Well, the eigenvalues are the possible result of the measurement. So now it means that if I have a box and I want to measure a measuring box, and I want to measure a system, then this box I can associate to this box an operator, okay, which is the observable associated to the measurement of this box, say measuring a spin, for instance. And the eigenvalues of this operator so this lambda here, will be the expected, the possible measurements, the possible results of my measurement. So so what I don't know, so I don't know, as we will see, I don't know what result I'm going to find, because quantum mechanics tells you you don't know, we come back to that, you don't necessarily know in advance what you're going to find. But what you do know, in terms of result, but what you do know is you do know what results you could find. These are the eigenvalues. These are the result of your measurement. So that you know. And you know, so these are the eigenvalues, so the possible result of the measurements, and the eigenvectors associated to a given eigenvalue are the possible states of the measurements. So it's the possible wave function, so sorry, here, of the measurement. So if I go back here to this example here, if I start from a qubit, but it's a wave function, I do something to it, a gate, so a rotation of a polarization state or whatever, I end up with a different wave function. So I end up with a different vector state, and so on and so forth. So you can see that the wave function itself changes, and I can associate a vector to it, a wave function to it, for each step of the way. So if I do that, for a given operator, A, which is a given measurement, I will find a result that would be the measurement I read on my box, and I will find now my system in a different way. So for instance, if I take, and we will take another example, but if I take a polarization state, I take a polarizer, I measure the result, so I know that now I have, say, polarization is vertical, then the state of my photon now is vertical polarization state. So two different meanings. So there's the result of it, and there's the state of it. Okay, because once again, the state is the ket, and the ket is related to the wave function, which defines the system. Right. So if I take an example, so here's an example. So here's I've got matrix A. So let's do that. So my matrix is 2, 3 plus 3i, 5, and 3 minus 3i. So this, in order for this to be an operator, we said that this has to be Hermitian. So this has to be equal to a dagger. Well, it is the case. Dagger, remember, it's the complex conjugate plus transpose. Complex conjugate, that means I would put a minus here and a plus here. And transpose, I would flip them, so the plus comes here and the minus go back there. So I would find, indeed, the same. So that's fine. So, okay, let's find the eigenvalues. So it's a 2 by 2, so a matrix, so I should expect 2 eigenvalues. So 2 results associated to it. So two eigenvalues plus 2 eigenvectors. So let's call them, so I call them A. So A, and the values, well, we can call them lambda. So, all right, so if we do this, we will have, not it. This, with the intensity matrix here, equals 0. This is going to be 2 minus lambda, 3 plus 3i, 5 minus lambda, 3 minus 3i. It's the determinant. Sorry, not the matrix anymore. So I take the matrix and I take the diagonal matrix made of these eigenvalues lambda, and I look for the determinant of that. So this is given by the product of these two, minus the product of these two. Okay, let me take my notes to make sure. Alors, is it? Yeah. Okay, so this would be so 10 minus 2 lambda minus 5 lambda plus lambda squared minus so 3, that would be 9. 3 squared, that would be 9, and then 9, and I've got minus and another minus, so that would be 9, if I'm not mistaken. Yep. So that's no, sorry, that's a plus. Sorry. So that would be lambda squared minus 7 lambda minus 8. Okay. So I can find. So this is a standard second order equation. So I can find the eigenvalues associated to it. So I would find. I'm not going to carry on calculation, but I would find two values, which are 8 and minus 1. And I can find the two, so I've got two eigenvectors, so two eigenvalues and two eigenvectors, which would be A1. There's an infinity of eigenvectors, but we usually take sort of the simplest ones. So in this case, one of them could be, so 1 and 1 plus I, and A2, which is going to be 1 minus I minus 1. Okay, so, oops. Let's try to. So, two things here. The first thing is that the eigenvalues are real. And that's very important. And again, we come back to the physical meaning, and that's what the footnote here is that emission matrices have real eigenvalues. And that's because these operators, which are supposed to be emission matrices, when I make a measurement, I measure a real value. Okay? I do not measure a complex value. There is no I. There's no 3I in what I'm going to measure. Okay? If I measure a current or a spin, or I will find a real value. A measurement is a real measurement. So that's an important condition, is that all the eigenvalues I will find to an operator, which is an observable, which will give me a measurement, have to be real values. It cannot be complex values. There is no such thing as a complex measurement outcome. first of all. And second of all, these eigenvectors, so we have two of them because we have a two-dimension matrix operator. They form an orthogonal, they are orthogonal with each other. So if I look at the inner product, remember, the equivalent of scalar product, but for our Brownian kets, then in this case, well, let's take more space. So the inner product of the eigenvectors would be A1, A2. So A1 is the bra, so is the transpose conjugate or transconjugate of A1. So that would be 1 minus I1, and A2 is this one. So is 1, is it's 1 minus I, and then 1 minus I minus 1. Minus 1 times 1 minus I. That is 0. And that's also a very important fact, is that operators and observables, the results are fine, or the eigenvectors, so the vector states after the measurement are orthogonal between each other. So in other words, there is there is a unique measurement associated to a unique state vector, and vice versa. Okay? Which makes sense, because again, if I make a measurement, I have an outcome. I don't have perhaps another outcome. No, I only have one outcome possible. This outcome has to be one of these values, and the state, the wave function after the measurement, has to be one of these. So these states in between them have to be mutually exclusive. They have to be orthogonal with each other. So operators, observables, makes measurements. So this apparatus will give us what is the result of our measurement and what is the state afterwards of our system. And that is linked to what we're going to see in a minute, the notion of the collapse of the wave function. And we'll see that in a minute. So let's go back to one of our physical systems. So let's talk about the spin state of an electron. So in classical mechanics, there is the notion of angular momentum. So if I take a spinning top, so I've got two here. So if I take spinning tops, so this is a spinning top. If I turn it, I can define an angular momentum, which is a quantity that goes upwards in this case, or along the rotation axis. And that would be the vectorial product, the mixed product of the speed of rotation, that way, times the vector or the position on the spinning top. So if I define a position here, I've got a distance r here, and if I spin it, I've got the speed going that way, and the mixed product between r and v gives me the rotation axis, which is the angular momentum of a spinning top. Okay, so I can have another one here. This one is interesting because it's much more tricky to have it straight up. So it gives us the fact that the axis of rotation is not necessarily in one direction. Oops. In fact, it's quite tricky to get this one working. Okay, this one is a bit easier. So those define angular momentum, which we have all the time in classical mechanics. So angular momentum, I can call it L. So this is defined by this vector here, which is, as I said, the mixed product, the vectorial product, between the position R from the center of the spinning top to the edge, times, or mixed product with P, where P being the momentum, which is m times V, remember. Sometimes angular momentums are called m as well, but in quantum mechanics, we usually like L rather than m. And by the way, so this is a classical quantity, but we can show that the units of an angular momentum are actually units of h bar, the reduced Planck constant. And in fact, the measurements, so the results that you make, so the quantum operator associated to an angular momentum are the results you find will be a certain numbers of h bar, okay, as we will see. So now this is a classical spinning top, like the ones I just showed. But there is, we can define the same angular momentum, so operator, a quantum operator, quantum version of it. We can put a hat on top, and we would have the position operator and the momentum operator and the angular momentum operator. And in particular, there is one that is interesting, is the intrinsic spinning of an electron. So electrons are, as we know, are negative charges, and they constitute the electronic cloud of an atom. But if I take an individual electron, which people can do, we'll talk about these technologies at some point, how people manage to do that. Not today, though, but at some point. They can manipulate a single electron. And the thing about electrons is that they have this property that they can, like this spinning top, they can spin on their own position. And like a spinning top, they can spin one way, so they can go around one way, or they can go around the other way. They have two possibilities of spinning. And since an electron is a negative charge, there is also so the classical way of interpreting that is that if an electron goes around itself, spin on its own position like this, as the electron is a charge, then what you have is you have a charge moving. And in electromagnetism, in physics, Maxwell's equations that we briefly saw, but whatever, these equations, one thing that, amongst other things that they predict, is that when you have a moving charge, a spinning moving charge, you have a magnetic field that is generated with it. So in this case, if the electron spins that way, you can generate, so it's what we call the right-hand rule. If I spin that way, my thumb here will give me the orientation of the magnetic field created by this spinning charge. So we can define what we call a magnetic moment, mu, a spin magnetic moment. And as I said, if the spin is along the axis, say, z, then as we just saw on a standard spinning top, I can rotate it one way, or I can rotate it the other way. So I can associate a spin, a magnetic field generated by the spinning, which we call the spin magnetic moment, which can be seen as a small magnet, basically, that we created, or that nature creates, rather, and we don't even have to do anything, because this is an intrinsic property of electrons. That's what electrons do, the spin, which gives us two possible outcomes. So either spinning this way gives us a magnetic moment upwards along Z, or a magnetic moment downwards. So we have two states. It can either be upwards for the angular momentum here, which is the spin, or it can be downwards. So it's not, so just a quick word. So the spin, again, is an intrinsic property of an electron, which doesn't mean that the electron cannot have an angular momentum. So the electron can also spin or rotates around an axis. So the view to see that is that if you take the Earth around the sun, so the Earth rotating on itself would be the intrinsic spin of the electron, and the Earth rotating around the sun is the angular momentum of the Earth, because it's like the spinning top is something that rotates along an axis. So we can define an angular momentum of the Earth going around the sun and rotating along itself, which would be the equivalent of the spin. So the total angular momentum, in general in classical physics, is the sum of the two. So it's the angular momentum L and the spin S. Let's assume here that the electron has only its own intrinsic spin, so I can make sure that the electron, so that's what people do, they trap electrons in a material, so they trap single electrons. So these electrons have no angular momentum. But the one thing you can't shut down is their intrinsic spinning. They always spin. So that means that you can make sure you only have one electron trapped somewhere with a spin, its own spin, that can be in two directions, so either spinning one way or spinning the other way. And that's very interesting, because these two states, well, is like the equivalent of the polarization state for a photon. If I say that this state is 1 and this state is 0, then I can have potentially my qubit state where I've got a 1 or a 0. Okay? Just a quick word, there is the relation between this mu, this magnet, this spin magnetic moment mu, and S, the actual spin, so the angular momentum S, which has values proportional to h bar, I told you. It's just gamma S, where gamma is the so-called gyromagnetic moment, gyromagnetic number, which is the charge Q divided by 2, the mass times the c, the speed of light, and times the number g that depends on the particle itself, because here we're talking about an electron, but you can have something else spinning as well. You can have a proton spinning, you can have anything else. The g factor here would change. But anyway, this is very physics, which we don't really care so much. What we do care is that there is this S value here, which is an angular momentum, which has values proportional to h bar. Therefore, and this is something I can measure, so if I take my spinning top, I can measure it in one way or the other. Therefore, I can associate an operator to it. So this operator will be Sz, operator Sz, which is what is the spin orientation, so upwards or downwards, of my electron. We can show, therefore, that this spin orientation has only two eigenvalues, right? Because if I take an apparatus and want to measure the spin of my electron, then I would only find upwards or downwards. The values are actually h bar divided by 2, plus h bar divided by 2, or minus h bar divided by 2. But forget the h bar divided by 2. What I have is two states. I've got an up state and a down state, which could be my 0 state and my 1 state of my qubit. So if I can control, and people do that, a single electron somewhere, if I can manipulate the spin of the electron, which people can do using magnetic field, you can orientate the axis of this magnet. That's what magnets do. When you put them, it's like a little compass in a magnetic field. It will follow the magnetic field, so you can manipulate these spins. Okay. So therefore, this is the equivalent of our polarizers and various optics with the polarization state. I can do the same here on the electron spin. It's just different techniques, different technologies. The fact is, I will have two outcomes, whether I measure it, either up or down, because that's it. Electrons are what we call fermions, and fermions have this property of having two values, opposite values for the spin, plus h bar over 2 or minus h bar over 2. So this would be the operators associated to it. These are the eigenvalues, which are the results. And this, by the way, the spin state here, if I rewrite it like this, I can put h bar over 2 in fact, factorize it, to put it in front. Then I would have 1, 0, 0, minus 1, and that's what I introduced before, the sigma 3 Pauli matrix that I introduced before, which we usually call sigma z, and you understand now why we call it sigma z, because it's the measurement of the spin along an axis which we usually call the z-axis for the North Pole axis of the Bloch sphere. We'll come back to that later. And in terms of gates, this Pauli matrix is a Z gate that we will see next week. So now, if I apply what we said before about eigenvalues and eigenvectors, what does this mean? Well, it means that so the spin operator S along Z with a hat for operator has two eigenvalues, two results possible, h bar over 2 or minus h bar over 2. It's either spinning upwards or spinning downwards with the rule of the what we call the right hand. So in this case, it would spin that way, so down state, in this case, up state. But if I have two eigenvalues, so eigenvalues, so two possible results only, I've got two eigenvectors associated to them. So one that I can call up and one that I can call down. Two eigenvectors, so up and down. I could find out what they are, but I actually don't need to find that out, because what is efficient or sufficient, sorry, for me at this stage and for what we want to do is that this property means that for h bar, that if I apply my operator to the state plus, so the eigenvector plus, then I find h bar over 2 plus. And if I apply Sz to my minus state, then I find minus h bar over 2. And what does that mean, applying this to that, this operator to this state vector, to this ket? Well, it's my measurement. So this, what this tells you, it says that if I have an electron spinning upwards, or spinning in such a way that the spin is upwards, then so he is in this state, I know that, because I prepared it that way, in a magnetic field, for instance. Then if I measure it, and that operation is matrix times ket is measuring, I measure it, then, as this is an eigenvectors, it will be found in the eigenvector state plus, of course, because it's spinning. I know already that I'm spinning it that way. So if I look into how it spins, then, then I know which way it spins. So I am in that state, but now I know the value. The value is h bar over 2. Likewise, if I prepared my electron spin downwards, I apply the operator, I measure it, surely I will find it that it's downwards. And the value associated to it will be minus h bar over 2. That's what it means. So applying the operator to the ket is making the measurement, and this is getting the result, and this is getting the state I find my system, and what state I find my system afterwards. As I started here, surely this is what I have. As I started here, this is what I have. So this, I could call it 1 for plus. This I could call it 0 for so upwards, for downwards. And that could be my 2, as I said, my 2 qubit states. But now, you could say, okay, well, that's good, but this is not a qubit. A qubit is the sum of the 2. It's the superposition of the 2. And you're right. But that's fine, because as these 2 states form a basis, we said that what can I remove? Yeah, this, I can remove that. Up and down actually they form a basis. In other words, the inner product up-down will be equal to the inner product down-up, and that would be 0. And the inner product up-up would be equal to the inner product down-down, and that would be normalized, and that would be 1. So these 2 eigenvectors, and that's what we said, they form a basis for the spin operator Sz. I will write it again. So in other words, what is the most general state of my spin? Is not that, nor that. Those are particular states. Those are fixed states, which is spinning up or spinning down. But the most general state is a superposition state of spinning up and down at the same time. It's the exact equivalent to our 2D vectors, to our vector in a 2D space, which is can be written as the combination of the two bases of the 2D space, so along x and along y. So here's the same thing, except that now it's not in space, it's in a spin state. And the basis is is up and down, upwards and downwards. So the most general state of the electron spin is psi equals some coefficient upstate plus another coefficient downstate. Okay? Which I can rewrite in a qubit notation, as in alpha 1 plus beta 0. And here we go. We have our qubit, but with electron spins now, rather than polarization state. So in other words, as opposed to a real spinning top, as in classical spinning top, before I make the measurement, I do not know, in the most general way, what is going to be the result. I don't know what the spin state is going to be. Is it going to be up? Is it going to be down? I don't know. So the most general state is a superposition state of the two. Or I can make sure, this is what we will see, with, for instance, what we call the Hadamard gate. We already saw that, well, you don't know, I haven't said it yet, but we already saw that with photons. I can prepare, I can make sure that the spin goes from, say, up to a superposition up and down, and becomes a qubit like this. And what it means is that now if I measure my state, so if I want to make the operation of measuring the spin state, then I will have a superposition of up and down. And all I can have is a probability of finding up or down. And as written here, the most general way will be a 50% chance of having up and 50% chance of having down. That's equal, and that's most likely what you want, equal probability of having one or the other. Okay? And in this case, alpha and beta are 1 square root over 2. So, measurements. Well, we have our measurements. Now I've got an electron spin, so most general case is like this. I've got an apparatus that will make my measurements. But as we said before, if I measure something, I will have one result or the other result. I cannot observe, I cannot see superposition. We said it with slits and other systems. There is no such thing as observing, measuring a superposition. What we can measure, though, is one of the two states with a certain probability. So I will find either up or down with a certain probability. In this case, which we just saw, the probability will be the squared of this coefficient, or the square of this coefficient would be 50%. So it means that I go from psi, which is the most general way like this. I make a measurement, okay, and I obtain one of the two results. So I only have up or down. And this is what we call the collapse of the wave function. So I wrote it like this, is a big up and a small down. What we say collapse in a sense that you went from these two possibilities to only one of the two. So you collapsed the wave function, you reduced the wave function to only one result, which is the observation you made, the measurement you found, the result you found. So, because yet again, you cannot measure the superposition state in real life. It has to be one or the other. So for that, you went from this state to one of these two. And for that, so it's the equivalent of what we saw much earlier on, of having your most general vector here as being the sum of the two components along x and y. And making a measurement means that you will project this vector, you will force the result to be either here, so the projection along x, or the projection along y. That's what it means, because either you measure you measure up or down. So a measurement is taking, so in the equivalent in 2D, is taking a vector and projecting it. That's the collapse, is that you take your vector and you project it. And that's your measurement, that's your end result. And this can be done by operators, which we call projectors, like P up for projecting along the up result, or P down, which is projecting along the down result. So these projectors, and we'll come back to that later on, because these projectors, as you can see, they look like what I call the outer product, because they are. So definition of the projector along plus. So this is not the momentum, it's projection operator, it's not the momentum operator. Let's put it like this. So definition, it's the so-called outer product, like this. So you may say, so how is this a projector? How is this? Well, this is an operator. This is actually a matrix, as we will see in a minute. So if it's an operator, so it's the measurement I make, is I go from this state to this state. That's what it does. So let's see if it does that. So I apply my projector to psi. Okay? So if I do this, I've got up, up. Now let me, because I'm going to be the wrong place, so let's write it somewhere else. Up. So projector on psi. So psi, sorry, projector, so up, up. So ket bra, not bracket, but ket bra onto psi. Okay. Psi, I can replace psi in the most general case by this, which I had before my measurement. Before my measurement, I was in a superposition of the two. That's the most general case. Then I would have up, up, sorry. And then I would have alpha up plus beta down. All I did is I took a psi and I rewrote it here. Okay, so I can distribute. So this alpha is a number, so I can take it out, just a number, and I apply this to that. So that would be, ket, bra, ket, bra, ket, plus, beta is just a number, I can take it out, beta, ket, bra, ket. So, oui, ket, bra, ket. Okay? Just distributing this quantity with this. Okay? And remember, when you take, say, this one and this one, we said the rule is you should have something like this, but that we define it as just a bracket when you take these two, or when you take these two. So you end up with two terms, but this term here, of course I erased it, but this term here is 0. Because this term is the inner product of the bra and the ket, which are up and down. And this is 0, because by definition, these two states are orthogonal, and therefore the bracket inner product of these two is 0. It's like the EX-EY is equivalent to EX-EY. And this is 0. This one, on the other hand, is not 0, and in fact is normalized as 1. So what I find at the end is I find alpha up. So the projection, this operator, which I define like this, being a ket bra, not a bracket, but a ket bra, which is the so-called outer product. This is an operator. I apply it to my psi. And by doing so, I end up with alpha up. So it is, by definition, a projector, because what it does is that I started up with psi in the most general way, being up plus down. I make a measurement, and I find up. So what I did, the equivalent of my measurement, is that I projected psi onto up state. And I find this, and if I want to know the state, so it's now the state is the up state, with a probability, except that now this probability, I have to renormalize it to 1. Because now the probability of finding up is 1, is 100%, because I measured it. That's why we said that again, the notion of collapse is I went from something that had 50% chance of being this one or this one to something that is now 100% chance of being this one. Okay? And that's a very important property of quantum physics that we need to use for quantum technologies. Once you measured something and found a result, then it stays that way, right? If you take your spinning top, make it turn and stop it in one direction, then you know this is it. This is what you have. And quantum mechanics tells you that now if I do the measurement again, so if I apply the projector again, if I apply the projector up, I will find the same thing, up. And if I apply down, I will find 0. So in other words, I know now I collapse my wave function to a certain result, and if I want to measure this again, so using the same apparatus, then I stay up and I will find up and up and up and up, unless I do something else to reset my qubit, to reset my state to a superposition state. Otherwise, that's it. So measurement in a quantum circuit, the measurement sign is given by this sign. As we will see, we already saw some of it. So if I take psi, if I make a measurement, I end up with the result m, and a state, and a vector state, psi, up or down. Okay. So this was for 2 states, up or down, but I can have, for a given operator, A, I can have a most general case, again discrete. I could have also an infinite basis, but we're not going to go into that. So I can have a discrete basis where an they form a basis for the operator A, so they would be the eigenvectors, so there would be n of them. And the most general state psi would be a sum of the Cn an, right? Where there would be C1, C2, and then C3, 4, 5, 6, and so on. And each of these Cn, the Cn squared here, represents the probability to find the result, the eigenvalues an. Okay? In this case, it was simple. There was only 2 cases, but you can have n cases. You can have n, so not just a 2D dimension state, but 3D, 4D, nd, with as many results, or as many measurements, measurement results that you can have as n. Okay? Now, if I apply this operator onto psi, so A, so let's do that actually. So I've got most general way, which is there you go. So now A psi would be a sum of Cn an. Those are coefficients, I can take them out. This matrix will be applied, the measurement will be applied to the ans. This, by definition, those are eigenvectors. So this will give me the eigenvalues times the eigenvectors. And so I've got sum of Cn, an. So the an are the expected outcomes, not just 2 now, they can be n of them. And they are the eigenvalues of these operators A in this case. And I can define So for the two states, so if I go back to the up and down, I can define the up state, probability of finding up state, as being the projection, or the inner product of the up state onto psi. So if I take this quantity here, up psi squared in order to have a probability, and remember, in the most general case, this is a coefficient, but the probability is actually the squared of that. Then if I do that for my psi state, where is it? Somewhere here. Then I end up with the probability alpha squared. If I do the same for down, I will find probability beta squared. And in a general case, if I do it for here, then I would project onto A. I would, take the inner product with AN, and I would find Cn squared. So we can do that. So if I take AN and apply it to psi, I've got AN, and then I have sum of the AN Cn, AN, okay? And so this would give me sum of the n Cn, AN, AN. Okay. Well, no, let's not do that. Sorry. If I take AN, and here we take another index, we will take M. Otherwise, it's not going to go. Then what I have is I have sum of M, Cm, AN, AM. Okay? But this is 0 if n is different than m, and is 1 if n equals m. Right? Because all of those, they form a basis. So all of those are the inner product of two vectors, so the bra and the ket, which are all orthogonal with each other. Because that's what we said, they form a basis of the operator. That's the eigenvectors do that. So if I take the scalar product, then those are 0, all of them are 0, except for one case when m equals n. So then this quantity is 1, because it's normalized. And in this case, I end up with Cn for n equals m. And if I take, so now the probability of finding An is actually the modulus squared of that. So it's Cn squared. Because remember, again, the most general case and the Cn coefficients here are complex numbers. So I have to take modulus squared in order to find a real number, which is the probability of finding An. And that is the case. The probability of finding An, we can see it here, it's Cn. Well, the coefficient is Cn, so the probability is Cn squared. Right. As we will see next time, so not next week, but next lecture, we can look into the... So far, we've talked about the measurement of the spin along the spinning axis, so along Z. But one question you may ask is, what about if I measure along another axis, along the x-axis or the y-axis? Well, those quantities do exist, those operators do exist. they call the Sx operator and Sy operator. And I can tell you what they look like. They look like these two matrices, which are anti-diagonal matrices, where you have for Sx h bar 2, and for Sy I h bar 2 and minus I h bar 2. And those, interestingly, are also the Pauli matrices that we define, the X Pauli matrices and the Y Pauli matrix. So those we will manipulate when we will, next time, when we talk about quantum gates. And we will see how these measurements are actually measurements, so not along Z, but along X or Y. And those will tend to influence the qubit, but in a different way. So for instance, if I take my upstate and I applied Sx to it, so here's what it looks like. My upstate could be 1, 0, and my downstate could be 0, 1, because we said it has to be an orthogonal basis, so I can take whatever I want as orthogonal. So here we go. It takes 1, 0, 0, 1, the simplest. So if I do that, if I apply Sx to up, then I end up with 0, 1. So I end up with downstate. And if I apply xy to down, I will get an I upstate. So what it means here is that for the Sx measurement, so measurement along x, what I do is actually I have an actual gate, the X gate, the Pauli gate, and it's the NOT gate. Remember, I mentioned that before, is that the X gate can be seen as the NOT gate. So what the NOT gate is it takes the up spin and put it down the down spin, and it takes the down spin and put it up towards the upper spin. So we start from up, we apply X as Sx or X, we obtain down. If we were to take up here, we would have obtained down. So it's a NOT gate. So you can see already, so the Sz, give us our qubit, so along the X, and now the S along the Z, and now the Sx is an operator that we can also use and measure the up or down state that will give us the NOT gate. So reverse, go from up to down. And for Y, it also reverses, but it adds a phase as well, an I phase, which could be interesting for various applications or algorithm as well. So you can see here these, I told you before, how these Pauli matrices X, Y, Z are very important, and we will come back to them later. Well, here we go. In these cases, by measuring the spin of an electron, so either along the spinning axis or along the X and Y axis. And by doing so, we have now the three gates, which are the X, Y, Z gates, which in a way do manipulate our electron spin, so our qubit. Right. So I'm not quite finished, but soon, because time is running out. One last concept before finishing for today is the concept of the mean value of a measurement. So what that just showed is that if I take, so let's have an operator A with eigenvalues an and eigenvectors an. So the most general case for the state of my system is going to be the sum of Cn an. Again, so here, this is psi. Is that psi is in a superposition state of any of the possible outcomes, and it's in is a state that can be written as a superposition of that can be developed in the basis of the eigenvectors an. So the probability of finding the result an, this is what we calculated here, is Cn squared. Good. But this is the probability of finding one result. But I could say, well, okay, this is for finding one result. But what I want to know is to know when I make measurements or several measurements on systems that are similar. Remember, I can't take the same one because once I measured, I collapsed it, I modified it. So I need to take one system, put it in the same superposition state like this, and then measure it each time. I can find an average number. I can find an average value, which we write like this, which is the average, which would be the average of the various results I will find. And this mean value, well, we know that from classical probabilities, is that the mean value will be the sum of the probability Pn times an, which is the value, the result I can find. But the Pn, or the P of an, is Cn squared. So the mean value is Cn squared times an, which I can rewrite Cn star Cn an. Now, if we make the following observation, and the following observation is that if I have psi like that, which is a ket, I can define the bra associated to it. So all I do is I do conjugate transpose. So conjugate is the conjugate of the Cn, and transpose is the transpose of the kets an. So they would be the bra an. And now if I take this by definition, if I say that the mean value of A is actually the inner product between psi A and psi, then I end up with my mean value. So let's do that quickly. Oops, sorry, oh, not that one. It's a scary one. So if I claim that this is, by definition, the mean value, then let's verify this. So now I take the bra psi. So the bra psi is sum over n Cn star an. Alors, let's put different indices. So m, like earlier on, m. And then I've got A times sum over Cn an. Okay? So this is the bra psi, and this is the ket psi. This would give me sum over m Cm star am. And if I apply A star to this, well, the an are the eigenvectors, so I will have an. So I would have sum of Cn an. Now, if I multiply these together, I will have two sums, sum over m, sum over n, times sum over n, of Cm star Cn times an, and times the bracket associated to it, so am an. And this, again, like earlier, is 0 if m different than n, and then 1 if m equals 1. So in other words, all of this is 0 all the time, except for one case when these two indices are equal. And when these two indices are equal, then I only have sum over n of Cn star Cn an times 1. This is Cn squared, which is what I defined earlier as being the probability Pn, which I wrote here, Pn. So I found this, that the mean, so this quantity I defined, this thing, actually end up being, well, the definition of an average, of a mean value, which is sum over all the possibilities of the result times the probability to obtain each result. So this is the mean value definition. And I just showed that this actually is equivalent to doing this, to calculating this quantity, which is the inner product between the bra psi and the result of A psi, which is the ket A psi. Okay? And this, by the way, I can write it in an integral form, like we did before, you know, this just today, this physical meaning I was talking about, and it would look like this. So psi star A psi. And this, as we will see next time, can be seen as a probability distribution of the value A taken over the distribution of the wave function, which is, well, exactly the definition of a mean value. And as an exercise that you can do for next time is you now take that and apply it to Sz. And you will find that the average value of Sz, for equal probability of having up or down, is going to be 0. Yeah, if I have equal probability of having up and down, the mean value would be 0. So you should be able to find that by applying this formula. Right, and I think with this I will stop for today. So thank you, and see you not next week, but in 2 weeks' time, where we will finish this part and start on to more quantum computing aspects with quantum gates. Thank you.